Hi guys, 3.5. Exponential growth and decay and modeling data. Exponential growth and decay is objective 1, okay? But modeling data is all 5. So we're going to be looking at, in objectives 2 and 3, you're going to get 2 new formulas. Nothing that you have to memorize, but you need to be able to recognize them and use them appropriately. Okay, let's get started. All right, so exponential growth and decay. Nothing really new here as far as solving equations you're going to find, but I want you to recognize this formula. Okay, the formula should look pretty familiar. It should look like, think about it for a second, the A equals PE to the RT that we've had in a couple of lessons now, I think in 3.2 and again in 3.4, or maybe 3.1 and 3.4. But A equals, this is read A naught E to the KT. Okay, so A naught that you see here and in this version as well. This is just showing you that it's a function of time. I would prefer it if they would have written A of T. Anyway, A naught is the initial amount or size. Okay, you can see that down here. It says A naught and then completes the sentence. Is the initial amount or time. It's when time is 0 for a certain situation. Okay, the big A on this side, or the F of T, if you're going to use this equation, is the final amount or a later amount that you're looking at, okay? It goes with a specific point in time. Reminding you about growing versus decaying back from lesson 1. We're going to be growing when our rate, that would be the K, is positive. What we talked about back in lesson 1 was if the base was bigger than 1, it grew most times, unless there was a transformation, okay, that would cause it to do otherwise. And if the base was less or between 0 and 1, it would decay unless there was a transformation to make it do otherwise. Well, the transformation comes if K is positive or if K is negative. If K is positive, we're going to grow because this base E is bigger than 1. If K is negative, we're going to decay. It will cause the normal growth for the E bigger than 1 base. It will cause it to reflect horizontally, and we will actually decay. All right, we're going to use this formula in a couple problems. So here's example 1 from your book, Modeling the Growth of U.S. Population. I want you to read through the problem. Read through part A. Okay, so read through it again if you need to. Pause, whatever. Part A, find an exponential growth function that models the data for 1970 through 2007. Okay, this is much like direct and inverse and joint and combined variation back from 2.8. You were told it varies directly. In this case, that told you how to set it up. This is saying it's an exponential growth. It's telling you the way our equation should look. And it should look like this. Okay? More specifically, when we are done finding this exponential growth function, we will have this formula, but an A naught value will be in there specifically, and it's going to be hard to get it on there, but a K value will be there specifically. A naught and K. Once we find A naught and K, then we can write our exponential growth function. All right, so if we read through this, figure 3.22 started in 1970. Okay, so the amount that we have in 1970 is the initial amount, A naught. So that's where we're going to start. Now we need to find our K. Just like in direct, inverse, joint, combined variation in 2.8, we had a set of information that we were able to substitute that would allow us to find our K. And that's what's going on right here. By 2007, it had grown to 300.9 million. They're giving us a second ordered pair. The 300.9 is going in as our A, and the T is 37. And you might be thinking, well, but I thought it was 2007. Well, the T is how many years from the start. 1970 represents time equaling 0 for this problem. And so think about somebody was born in 1970. How old would they have been in 2007? That would be 37 years old. So that's where the 37 comes from. At this point, you have an equation that you could have had in 3-4. Could have asked you to solve this. Did ask you to solve it, not for a K, but asked you to solve it. So I'm not going to hold your hand.
This is the last one.
Cool, buddy. I'm not going to hold your hand walking you through this, okay? I'm going to show it to you. I'm going to remind you that you do not want to round your numbers on your calculator. So if you put this in your calculator and you get a decimal, you better be prepared to use the full decimal the whole time, okay? So I would just leave it as a fraction as they have. Solving for K right here. And we find that K is this exactly. That's crazy. But it's approximately 0.011. And that would be 1.1% if you were asked to have it in a percentage form. All right. Now remember why we found K. K was not the end of our problem, but it was a piece that we needed in the puzzle. So if we put that in, 203.3 e to the 0.011 t. My preference would still be to leave that, to store K in my calculator or leave it long written somewhere else so that when we go to part B, by which year will the population reach 315 million, we have the long K and not the rounded K.
So let me see if it will work.
All right. So by which year? That means we want to find the T that will give us a population of 315 million. All right. And now we have an equation that was identical to the form we had when we just found K. So all of the steps are going to be the same steps. You can just bet that if you are asked,
I got a crab.
cool, buddy. If you're asked to write a prediction equation, you just bet that you're going to have to use it. Or on a quiz, it might not say even write the prediction equation. It just might ask you to find how long, but you have to write the prediction equation to figure out how long. Okay, so T equals 40. And I guarantee you that if you were to substitute, or if on Math Excel, you were to put 40 in as your answer, it's going to be wrong. Okay, let's look at the wording so we can know why. The wording says, by which year will the population reach 315 million? So is it by year 40? You know, like 40 AD? Or what does it mean? Okay, and it's actually by the year 2010. Okay, I thought I had this in here, but the year would be 1970 plus 40. Okay, so the year would be the year 2010. Some of you may have been tricked by that on a previous assignment, Math Excel wise. Okay, use the fact that after 5,715 years, this is example 2, same kind of problem. You can see the same thing starting down here. After 5,715 years, a given amount of carbon-14 will have decayed to half of the original amount. Find an exponential decay model. So we're going to use this, but if it is decay, then we have something we can expect. We will expect for our rate, our K, to be negative. Okay, just know that in my mind. If it's decay, then K is going to be negative. All right, so how do we do this? This half of the original amount. Buddy, they're not blood oranges, no. All right. So watch this. Try to wrap your head around it. Don't just quit on me. We start with this formula, A equals A naught e to the KT. And it said we need to find out, or it took 5,715 years. I hope you're recognizing that as your T. But it's going to decay to half of the original. Okay, so watch what we have here. In 5,715 years, the final amount is going to be half of the original. Doesn't that look weird? Not for long, my friends. Okay, we need to figure out the K so that we can get our exponential decay formula. How quickly is carbon-14 decaying? This would be half-life from chemistry. I'm not sure Chem 1 or Chem 2. Okay, so we need to find K. So what we would have done is normally we would divide away the A naught. And if you divide away the A naught, you're going to have 1/2 e to the 5,715 K. All right, A naught is 1/2. Now, one thing you can do if you would like in problems like this is you can just choose and say, I'm going to say they started off with 100 as my A naught. And if this is 100, then half of 100 would be 50. And then you would divide by 100 and get 1/2. Or let's say you're saying they're going to start with 4. Half of 4 after 5,715 years would be 2. And when you divide by 4, you get 1/2. Okay, so you can stay general, which is the preference. But if you need to, just say A naught is and give it a specific value. Now we need to find K, and it's that same question. Where is it? In the exponent. How do we get to it? Take the natural log of both sides. And we find that the rate of decay is approximately -0.000121. Okay, so it decays very, very slowly. It takes almost 6,000 years for half of it to decay away. All right, now here is the formula, and I want you to notice a difference from example 1. In this one, we have A naught staying A naught, and that's to allow you to substitute any initial amount. We weren't told a specific one. I told you could make one up, but that was just for the purposes of finding K. But any A naught there. Let's go on to part B. All right, so 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bedouin herdsman. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. Estimate the age. I hope you recognize that this is asking you to find time. Okay, so 76% of the original. That's the final amount, is 76% of the original. Okay, on the other page, when we had something that said half of the original, we put in A naught over 2 as our A. Here, 76% of the original is going to be 0.76 A naught. All right. We're solving for T here, so we're going to divide both sides by A naught. It doesn't matter what the initial amount was. That's what this process is showing us. It divides away. Natural log both sides. You should be getting really, really good at this by now. And so it's saying 2,268 years. And this was really 2,268 years before 1947. Okay? Okay. Thanks. Love you too, babe. All right. So, objective 2 is using logistic growth models. This is where I said we were going to have another formula in here. And here we have it. The mathematical model for limited logistic growth is given by, and we have these two formulas, this one showing f of t, this one showing a. Okay? No differences. They won't forget that, I'm sure. All right, so you need to start recognizing now this setup. It's going to look weird and kind of scary.
And I'm not joking.
Mar, that's enough, babe. It says, you know, that A, B, and C are constants, and C is greater than 0, and B is greater than 0. You don't have to worry about that. This is what the graph of each of these will look like, okay? They kind of make this S shape. From Biology 1, you might recognize this as an S-shaped curve. This is where it grows exponentially in the beginning, but then it starts to level off because there's a limiting factor, okay, that causes it to start leveling off. C is your limiting factor. Okay, we're going to have problems that say, what's the limiting factor or the limiting amount? And that's going to be the C, whatever number is on top. All right, let me show you what's going on. Modeling the spread of the flu. Isn't that appropriate? Okay, so the function f of t equals 30,000 over 1 plus 20e to the negative 1.5t describes the number of people f of t who have become ill with influenza t weeks after its initial outbreak in a town with 30,000 inhabitants. A says how many people became ill with the flu when the epidemic began, how many people were ill by the end of the 4th week, and what is the limiting size or factor, limiting size of f of t, the population that becomes ill. I highlighted C because I would do, if it was me, I would do C first. The limiting size. Look back here. The limiting factor or the limiting size is your C. Okay? So the limiting size of this is going to be 30,000. Think about that. You have 30,000 people in the town. You can't have 50,000 people who get sick with the flu in this town if the town only has 30,000 people. 30,000 is the limiting size. Let's talk about Part B next. Okay? Part B. How many people were ill by the end of the 4th week? Well, T is measured in weeks. We're going to do F of 4. So after the 4th week, 28,583 people were sick. Yikes. Okay, let's back up to A. A says how many people became ill with the flu when the epidemic began. What began means is time equaling 0. Okay, so you got to recognize that so that you will substitute in correctly. See that down here? Time equals 0 right there. Okay, so on your calculators, guys, make sure you're doing this. Make sure you're seeing that you really get 1,429. If you don't, it's probably because your calculator does not know that you intended to have 1 plus 20e to the in your denominator. All right. What I want you to do is calculate the denominator, press enter, and then say 30,000 divide my answer. Okay, this is what they've done. They've calculated the value of the denominator, and then they divided 30,000 by 21. All right, do not type this all in your calculator and press enter. You will be sorry. Newton's law of cooling. I have my cup of hot cider here today. Newton's law of cooling, okay, what it does is it will give you the temperature of an object after a certain amount of time it's been taken out of the freezer or taken out of the oven or the microwave or whatever. A heated object, how fast or what's the temperature after a certain amount of time. So T is the temperature after a certain amount of time. C, you can see, is the constant temperature of the surrounding medium. So if you take it out of the freezer, C would be your room temperature. If you're putting something into the refrigerator or the oven, then C would be the temperature of that, whatever's surrounding it, okay? Normally, it's room temperature for our problems that we look at. T naught is the initial temperature of the object that was heated or that is being heated. So if I take something out of a 350-degree oven, so let's say it's 350 degrees when it comes out. That's your T naught. It comes out into a room that's 70 degrees. 70 would be your C. Okay, so cake removed from the oven. It has a temperature of 210 degrees. It's left to cool in a room that is 70 degrees. After 30 minutes, the temperature of the cake is 140. Use Newton's law of cooling to find a model for the temperature of the cake. What's the temperature after 40 minutes, and when will the temperature of the cake be 90 degrees Fahrenheit? Let's start with part A. Okay, based off of this, I want you to read through the problem again. What do we know? We were told 210, we were told 70, we were told 30, we were told 140. How do those numbers fit into the problem? Okay, so the 70 was the temperature of the room. That's the surrounding temperature. So our C's were both 70. The T naught was the initial temperature of the cake when it was removed from the oven. That was 210. So they did 210 minus 70 to get 140. All right, we cannot add 70 and 140. Don't even think about that because the 140 has the e to the kt. So where did the 30 and the 140 fit? Because this 140 is not that 140. Okay, I want to be really clear about that. So what we're going to do, again, like we did with growth decay in examples 1 and 2, is we are going to use this set of information, 30 minutes, 140 degrees, to find the K. Same process. Subtracting the 70, dividing by 140, we have a half. Natural log of both sides. I'm getting bored with this. How about you? Kidding. So the K is negative 0.0231. Okay, K negative, that should tell me that this object is cooling off. Make sure that makes sense in the context of your problem. The actual formula is 70, the room temperature, plus 140e to the negative 0.0231 T. Okay? And again, this 140 came from taking 210 minus 70. That's going to be a formula that we are going to use now. What's the temperature of the cake after 40 minutes? Plugging in the 40, finding that it's 126. Make sure your calculator knows that both of these values are in the exponent. When will the temperature of the cake be 90? Okay, so the final temperature is our 90. And again, hello, solving for T. So after 84 minutes, the temperature will be 90 degrees. Okay, choosing an appropriate model. We're going to have some scatter plots. We're going to have to say what kind of function would best model it. So back in chapter P1, we looked at like quadratic models, linear models, cubic models, quartic models, trying to decide which one it is. Now we need to throw into the mix exponentials, logarithmics as well. So we have here an exponential decay, exponential growth and an exponential decay. The telltale sign of that is you have this leveling off horizontally. We have this horizontal asymptote, okay? Exponential growth, exponential decay. Here we have what looks more like a vertical asymptote, and it's not leveling off, it's just increasing less sharply, okay? Increasing at a decreasing rate for you econ people. That would be a logarithmic, and then this is a decaying logarithmic, where we have this vertical asymptote, and then it's decaying here. All right, choosing a model, so we're going to look at this, and we're going to decide what does it look like is going on. Does it look which of these 4 graphs do you think that looks the most like? Okay, to me, it looks the most like one of those logarithmic ones. Okay, so you're just kind of looking and seeing which one you think would model the best. We could model it with an exponential or a logarithmic, but which one we think models it the best? This one looks like it's starting to increase a little more sharply. I know it's leveling off there a little bit. So I would say this one would either be more exponential, at least for the part we can see. If you're thinking logistic, that would be my best bet. All right, and now objective 5. Not going to take very long on this. It's really not something we use very often. It's just something we can do. So we want to show you that we can do it. Okay. Modeling world population. That's what this last example was about. Okay, and we have this formula. G of x is 2.569 times 1.017 to the x. Okay, this will model the world population in billions, x years after 1949. So 1949 is year 0. Rewrite the model in terms of base E.
Hi, this is Lori. David.
Mom, Nathan.
Leave us a message and we'll call you back.
All right, I'm going to keep going. My cell phone's probably going to ring in a minute too. Anyway, so y equals ab to the x. We can rewrite it with a base e if we wanted to think about it in that a equals a naught e to the kt format. Okay, we do that by taking advantage of that inverse property back from, I think, 3.2, the inverse property that said if you have e to the natural log, these cancel out. Well, if we want the e in there, we can do an e to the natural log. So if you have 2.569 times 1.017 to the x, that is equivalent to 2.569 times e to the natural log 1.017 times x. Okay, I'm not saying that this is something you'll want to do all the time, but it's something I want you to know that you can do. By no means is it a focus for us as just one of the priority things. It's more of a, hey, guess what? You can do this. Okay, that is lesson